So the parallel axis theorem allows you to transfer the moment of inertia to any axis parallel to the center of mass. So this is a two-dimensional conundrum, but it's just a simple shift. The reason the math works is immaterial. The math works. So to use the parallel axis theorem, you simply start with the moment of inertia of the center of mass. Now let me be really careful here. You start with the moment of inertia for the center of mass, and then you add to it a shift. I'm not going to be writing shift distance much longer. I write it because, depending on your textbook or which year the equation sheet is here, they write it as I center of mass plus mr squared or mx squared. And I just don't think I can take it. If somebody says x or r or radius or what does x mean, I just don't think I can take it. So you understand that I'll write shift distance for a little while longer, but the first person who says, well, what radius do we use, probably deserves to put the head in the fan. Fair enough? But after a while, I'm just going to start putting r squared in there because that's probably what's on your equation sheet. So let's pick one of these. So we're going to shift it from the center to a distance L over 2 away. All right. Moment of inertia about the center of a rod is 1/12 ml squared, and I'm shifting it by a distance of L over 2 quantity squared. That's it. That's the answer. You can clean it up, and when you do, you'll find out that this is 1/3 ml squared. And yes, it's the same as the point about an end. That's the way the math works. If you shift it this distance, well, it's still the same kind of problem. So that's 1. This will be 2. We'll get the new moment of inertia starts at 1/12 ml squared plus L squared. All right, you're just shifting a distance L. What's that? Well, it looks like it's going to be 13/12 ml squared. Now, here's where people were getting mistakes in the last class. If I want to shift it to this point, well, that's my shift distance. Right, from the center of mass to an axis that is parallel to the center of mass. I still have to start from the center of mass, so this has to be 1/12 ml squared plus I need to find my shift distance. I'm thinking the Pythagorean theorem. So I see 1/2 L squared plus L squared to the 1/2 power. Now, all of that is just 5/4 L squared, right? No, 5/4 L squared. 5/4 L squared to the 1/2 power. So, can we see that it's a square of a square root? So I'll just get rid of that square and put 5/4 L squared here. And I don't want to do the arithmetic. You guys understand why it's 5/4, right? Well, I see 2 nods, but I see people with that same dull kind of look that you see like on a livestock face. You know, looking at like a motor vehicle, wondering, wow, that looks neat. Either way, that's how you would do it. I will still need common denominators. And I think a common denominator here of 12 works. So 1/12 ml squared plus 15/12 ml squared gives me 16/12 ml squared, or 4/3 ml squared is the new moment of inertia. And I hope you're seeing that the ml squared portion is beginning to dominate the moment of inertia. It's becoming closer and closer to a point mass as we get further away from the object. That's not unintended. But there was somebody in first period who said, or sixth period who asked, could you just shift from here over? No. You can't start from the 1/3 ml squared and shift that way because that's not the center of mass. The parallel axis theorem is proved through the center of mass, not through any other axis. So mathematically, you might get the same answer. That's probably more happenstance than anything else. Do everybody understand? So now an argument can be made that you're shifting it twice, so doesn't it work? Just be careful. Use the parallel axis theorem as intended. All right. If we look at the problem as stated, let me try and set it up so we have something here to work with. Does that look like 45 degrees? Close to it, maybe? Good enough for you guys? When we consider that we're starting from, a reference level that's around the middle of the rod. And that's kind of what we're trying to do, is start at somewhere near the middle of the rod. And recognize that we have shifted the center of mass from there to here. You're going to have to find a way to figure out what this height is in dealing with the gravitational potential energy. Also, in dealing with the acceleration, you're still doing that torque, you'll have to deal with that angle. That's the only way in which this problem is different than when we did it by pulling it back 90 degrees. So I would expect that it's traveling slower and that the acceleration is less than when we did this problem for a situation in which we pulled it 90 degrees. But when the object makes it all the way to the bottom, it has some angular speed. And if you did this problem, or did the problem when it was pulled from 90 degrees and went down, we know that there's also some unbalanced upward force that causes a centripetal acceleration. Right? This is the problem that we've already done. When they ask what is the tangential acceleration when the rod passes the vertical, they're leaving something out. And this is why I want to be careful. Tangential acceleration would be the acceleration tangent to the object, which would mean we're talking about an acceleration in this direction. Not to be confused with a radial acceleration, which would be an acceleration along the radius. Centripetal acceleration is, by definition, a radial acceleration. If I had been asking that, you could find it by doing omega squared times r. The problem is, this would probably be center of mass. That's what we would have used to do the problem because the forces are acting on the center of gravity. But the tangential acceleration could be the tangential acceleration of any point on the meter stick. Without telling you which point matters, there's any number of tangential accelerations. If you don't understand why that's true, look, this point, when we release the meter stick, or whatever this is, has a velocity of 0, but is accelerating. And we know that when it makes it down here, it will have a velocity in this direction. A tangential acceleration acts on this point of the rod to change its linear velocity from 0 to something else. That's the linear acceleration. And therefore, it is acting tangent to the object. Do you understand? That means that there's not only a tangential acceleration here, but there's a smaller tangential acceleration here. Because that object, this part of the object, won't be going as fast when it makes it to the vertical. The issue is that when this object becomes vertical, at that instant, the net torque is 0. Because the two forces acting on the object don't cause a torque. We have two forces. There's a force here acting upwards on the pivot point. There's no torque there because that force is at the pivot. Torque arm is 0. The other force is acting at the center of mass and is downwards, mg. Although there is a torque arm here, length L over 2, there's no torque because the angle is 180 degrees. So for this instant, when it's very much at the bottom, the net torque is 0. If the net torque is 0, the acceleration is also 0. For that moment, the object is not speeding up or slowing down, it's transitioning through the bottom. Therefore, no part of this meter stick is experiencing any tangential acceleration. It's all experiencing radial accelerations. Now, I have a special person in the room, a person whom I have made fun of a couple times. The golf club actually assumes a shape that looks like this. So when they actually have their arms straight downwards, the head of the club isn't making contact with the ball yet. It's when they slightly pass the club that happens. And this is actually storing potential energy in the club for when it snaps at the bottom, giving them slightly better impact with the ball. The physics is actually pretty incredible. But part of the problem is that there's a tangential acceleration. This is applying a force to each piece of the rod. And that force doesn't always cause enough of an acceleration for the rod to stay together the whole time. So this is why you ask questions about the tangential acceleration. It actually plays a role in the way lots of things are. Baseball bats do the same thing, not as much because of the way in which baseball bats are shaped and the way they're structured. If you ever watch any videos of accidents when trying to knock down buildings, you'll see that the buildings tend to break somewhere in the middle because the whole building can't just fall down. There's not enough force to pull the top down faster than gravity can, so they tend to separate. Look up. Usually, we're talking about chimneys and towers that will do that. They'll fracture halfway down. So, I have no intention of explaining what I'm doing. If you want an explanation, I'm actually wondering why I even post any videos. The only difference between this problem and the one in class is this is M and not 2M. That is the absolute only difference. So here we go. There are two forces acting here. Tension, and I'm going to put tension 2 up and 2 mg down. There's two forces here, tension 1 up and mg down. And I'm going to make this the positive direction. So my pulley is experiencing a variety of forces, but the ones that matter will be tension 2 here and tension 1 here. So the box on the right is experiencing T2 minus 2 mg, which is going to equal 2 ma. Box on the left, T1 minus mg equals ma. These two a's are the same. Moving on, net torque on the system is going to equal I alpha. It is a disk of mass m, radius r. So I'm going to treat this as a disk, 1/2 mr squared. And I'm going to go ahead and sub in alpha over r because I believe that all the accelerations are linked together by the radius of this pulley. Now, dealing with the two torques act at the edges of the disk. So my two torques are going to be, hold on, let me give myself a little bit more space. Now let's see, in the direction that I have here, r times T2 minus r times T1. All right, I have set up my three force and torque equations.
What is it T2 minus 2 mg with the direction?
Oh, you're right, I should probably flip those since I made downward positive. So here we go, 2 mg minus T2. All right. I have three equations, and I have three different ways of getting the acceleration. I believe if I'm careful, I can cancel out all of the r's in this function just because of happenstance, and I get 1/2 ma here. And it's not happenstance. It was constructed this way. So with that, I can bring all of those things together. And so that's what I will do. add them all up, and I will get on one side 1/2 m. Actually, I'm just gonna collect the MAs. 1/2 plus 2 plus 1, all times MA. On the left side, the tensions all cancel, and I get 2mg minus mg. So it looks like I have mg equals 2 plus 1 is 3, plus 1/2 is 3.5, or 7/2 MA. Cancel the m's. A is going to be 2/7 G. Yep. Which is B and not C. We can find the angular acceleration. The angular acceleration of the disk is directly related to the radius of the disk. So the angular acceleration is going to be 2g over 7r. And that'd be the angular acceleration, but that's the answer to B. And he had asked for the answer to C. All right, enough of that.